to specifically focus on sampling distributions for X bars, sample means. We talked before of what a sampling distribution is. It's taking a sample, calculating the mean, and write it down. Then you calculate another sample, take another sample, calculate the mean, write it down. Take another sample, calculate the mean, write it down. And do it again and again. You have a list of all these means, all of these X bars from a whole bunch of samples. And when you have that list of all those X bars from all those samples, and that's the sampling distribution. If you put it in a histogram and you look at it, that's the sampling distribution. And we found out it ends up being normalish. So we're going to talk about sampling distributions for means and the central limit theorem, which is the fundamental theorem of all of statistics. Without it, we wouldn't have the course. So let's talk about how the CLT comes about, because it's baffling. So we're going to talk about a bimodal population, and hopefully at the end of this, you'll understand why, even with a bimodal population, the sampling distribution is still normalish with large enough sample sizes. So, imagine a bimodal population. So what these are heights of human beings at a daycare. Heights of human beings at a daycare. Notice, so a human being walks by, and it's a child who's a little bit under 3 feet. I put their height here. Or suppose it's heights of human beings at all daycares in America, just this big population. Okay? Notice, we have a bunch of people that are around 3 feet, and then some people that are between 5 and 6 feet. Those are probably the daycare providers and the teachers, and those are probably the children that are in the daycare, right? Let's say maybe it's a preschool or something, I don't know. But anyway, it's a bimodal population, definitely. And if I went and took a sample, now here's the big confusion. People are like, oh, the central limit theorem says if you take a sample from a bimodal population, the distribution of your sample will be normalish. No. The distribution of your sample is going to look like your population. So if your population is bimodal, if I go and take a sample from this, it's going to look a lot like this. I go out and take a sample of, let's say, 64 individuals. I'm going to find a bunch of students and some teachers. So my histogram, the distribution of my sample, will also be bimodal. And that's cool. And then I take another sample. And I get some students, and I get some teachers. Maybe I get a lot of teachers in this group. And I take another sample. And I take another sample, and I get some students. Every sample I take, I'm going to get some students and some teachers. Every sample is going to be composed of probably some students and teachers. And so if I go to a bimodal population, and I take a sample, I'm probably going to get a bimodal distribution for my sample. So if the population is bimodal, your sample is going to be bimodal. But that's not what a sampling distribution is. You need to know what a sampling distribution is. We're not talking about the sample, the distribution of a bunch of samples, because look at it. Here's the distribution of a bunch of samples. There's the distribution of sample 1. You can see the distribution of sample 2, sample 3. Oh, I'm going to take another sample. Oh, you're a little kid. Okay, you're an adult, another adult, another adult. Some more kids, some more adults, okay? And so I have a bunch of people around 3 feet, a bunch of people between 5 and 6. Again. But a sampling distribution, remember what you do? You go out there and you calculate the X bar. What is the X bar? Remember on a histogram, the mean is the balancing point of the histogram. So the population, in this case, we'll say the population, if I found the balancing point on the population, it would be right around here, around 48 inches, about 4 feet. That would probably balance these things and keep them in balance. And every one of these also has a balancing point. So I'm going to find the balancing point for each one of these. So let's see, this guy would balance, that would be probably like right around here. That would balance there. And that would be the X bar. And this next guy would probably balance around, I don't know, here. That would be the X bar. And this guy would probably balance around here. That would be the X bar. And this guy around here would be the X bar. Notice X bar. Notice all these little triangles, or all these X bars, right? All of them are pretty close to the middle, aren't they? So I take a bunch of X bars. What you need to imagine is making a sampling distribution. So see these samples? Imagine if this paper or this board went up forever, and I just took it and I kept sliding it up and taking another sample, and you can see all of these distributions of all these samples. So imagine these piled up. Imagine this on like some scroll or like this parchment paper, and like you could roll it up like a shade, and it went way up, and I looked up and it was like, whoa, and there was like a mile of all these little lines with a mile of histograms. And then you look at those histograms and you focus in on all the balancing points. And imagine if there was a button, and a button that said this, X bar drop. And what I did is I hit the button, bam! And right when I did that, all of those X bars, all of these X bars fell straight down like this. Boom! And the X bars would all fall down, and all of those X bars would land in a pile. They'd all fall down into a pile, and I'd have a pile of a bunch of X bars. That pile of X bars is the sampling distribution. That's what we're talking about. The central limit theorem doesn't talk about an individual sample or the distribution of a couple samples. The central limit theorem talks about the sampling distribution, the pile of all the X bars taken from a whole bunch of samples. They all fall down from all of those samples. They land in a pile. And that pile is always, with large enough sample size, normalish, centered at the true mean of the population, 48 inches. And the standard deviation ends up being this mean of the X bars is the true mean, and the standard deviation of the X bars is just the population standard deviation divided by the square root of the sample size. Always. So in this case, the mean is going to be 48 inches, the mean of all the X bars. The standard deviation of all these X bars is going to be the population standard deviation, 16 inches, all over the square root of the sample size. I took samples of size 64, so 64, which will be 16 over 8, which will be about 2. So 48 inches, 49, 50 inches here, 46, and I go up to 52 inches, and 44 inches. So I'll end up having this pile, all of them pretty much near the middle, and 68% of my X bars will be between 46 and 50. 95% of my X bars will be between 44 and 52. 99.7 of my X bars will be between 42 and 54 inches. Most of my X bars are going to be in there. So the central limit theorem, what it talks about is the distribution of X bars, not the distribution of a sample or the distribution of the population. So don't mix up that vocabulary. The population here is bimodal. The distribution of pretty much most of your samples will also be bimodal. But the sampling distribution, the distribution of a bunch of sample means, a bunch of X bars that you took from all of those, a bunch of balancing points, that thing is the thing that's going to be normalish. And sometimes it's written like this. It's going to be approximately normal, centered at the true mean, with the standard deviation of the population standard deviation over the square root of the sample size. That's what the central limit theorem says. It talks about all those X bars, not about individuals. See, I just threw that at you. All right.